Okay guys, so here we will continuing our session. Suppose q into q1 is equal to c upon a is equal to c upon a. So how to make it to make it a by c, so we have to do what? To make it a by c, we have to do what? Suppose a by c is equal to 1 upon q into q1. Okay, if we inverse this, that means 1 upon q into q1 means a upon c is equal to 1 upon q into q1 means after inversing this, c upon a is equal to q into q1. Okay, q into q1 upon 1. Okay, now so in that manner, so we can prove now. So it is a singular process. So that's how we can solve this. Okay. So I don't know. There is here is one postulate. So how to make it a by c? This is coming c by a. So is okay. So there's saying that a this. So it can be c by a by c, both can happen. Okay, so this is the significance of both. Like it can be a by c or c by a. It can be both. Okay, so I think we are done. You can erase this. You don't have to note down this part. Okay, you don't have to note down this part. Okay, you don't have to note down this part. Only you can do what? Note until this part. Okay, so let's move to the next subset of theorem 1, which is the third one. They are saying subset of third one, which they are saying okay, if a by b and a by c, then a by bx plus cy, for any integer x and y. Okay, so here we have to understand what they are actually trying to say. Okay, a by b and a by c, then a by bx plus cy for any integer x and y, if a by b and a by c, then a upon bx plus cy for any integer x or y. Okay, for any integer x, y. So now we have to prove this. I hope you guys all understood the theorem. When we will prove it, I hope we all understood actually what they're trying to say. Okay, hence they're saying if a by b and b by c, no, a by c, b and a by c, okay, then b is equal to aq. B is equal to what? B is equal to aq. Okay, and c is equal to aq1. Okay, so q and q1, these are both integers. Okay, and q and q1, suppose they are real numbers. Z, we denote real number with what? Z. Okay, now bx plus cy, bx plus cy equals to a into qx Okay, one second. Do one thing. Okay, we will move slowly. We don't have to hurry. Okay, we will move slowly. Suppose B is equal to a q. Okay, and q1 and c is equal to a into q1. Okay, so q and q1 both are integers. Q and q1 both are integers. These are what? These are integers. Okay, these are what? Integers. Now the q and q1 is similar to what? Is similar to z. Okay, we all know that z is a kind of real number, that denotes a real number. Okay, so how oh god, my ink is gonna end here. We have to pour ink. No. Okay, suppose for okay, so suppose for q into q1, for q into q1 is equal to z. Okay, okay, so now we have to, so now here we have to do what? We have to understand what this actually trying to say. This z, what's this? What is the meaning of this z? Okay, what is the meaning of this z? Okay, suppose this is a kind of z denotes, I think, real number. No, I hope z denotes real number. Okay, it doesn't matter. Okay, this is q and q1, q1. Okay, these are all real numbers. Now the thing that's saying that, okay, guys, have you noted it? Okay, note it down. Pause the video and note it down. Then we will move to the solving part. Okay, then we will move to the solving part. Okay, then we will move to the solving part. Note it down. I hope you guys done. Okay, so here okay, now hence bx plus cy, bx plus cy is equal to a into qx plus q1y. Okay, qx. Okay, suppose bx cy. Okay, we know that b is equal to aq. We know that b is equal to aq, and c is equal to what? C is equal to a into q1. Okay, these both are integers. Q is integers, q1 is integer. Okay, q is integer, q1 is integer. In the same manner, b is equal to aq, c is equal to aq1. Okay, when we put this value in this equation, then this comes. Okay, then this comes. So hence we can say that a upon bx plus cy, a upon bx plus cy. Okay, a upon bx plus cy. Okay, not this is a upon. Okay, this is a divided by bx plus cy. It can be bx plus cy by a, or it can be a by bx plus cy. Okay, it can be both. It can be both. Okay, it can be both. It can be both. Okay. Now we are done with the third subset of theorem 1. Third subset of theorem 1. Now move to the fourth subset. Okay. Now move to the fourth subset. Now move to the fourth subset. Okay, the fourth subset is saying if fourth one, if A by B, B not equals to 0, then A less than equals to B. So now this is a theorem, subset of the theorem. Okay, here if A by B and B not equals to 0, then A less than equals to B, A modulus less than equals to B modulus. Okay, A modulus less than equals to B modulus. Okay, now we have to understand that if A by B, if A by B, B not equals to 0, then B is equal to AQ. Okay, B is equal to AQ. Oh, sorry. Yeah, B is equal to AQ and Q not equals to 0. Okay, guys, my writings are visible. I hope it is visible. Hence, they are saying that B is equal to modulus of AQ. Okay, so we can write it as modulus of A, modulus of Q, as Q is not equals to 0. As Q is not equals to 0, so if it not equals to 0, then it should be greater than equals to 1. Okay, greater than equals to 1. Hence A modulus is less than equals to B modulus. Okay, so now we have to understand the proof. Okay, I hope you guys understood the theorem that if A by B and B not equals to 0, then A modulus is not less than equals to B modulus. Okay, here they said that if A by B and B is equal to 0, then B is equal to 80. We all know that Q is an integer. Q is what? Q is an integer, and Q is also not equals to 0. Q is also not equals to 0. Hence, B modulus is equal to modulus of 80. Then we can break it into modulus of A into modulus of Q. Okay, suppose Suppose modulus, what is the function of modulus? We all know modulus absorbs the power of any integer. Okay, the power of any integer. Suppose its power is, suppose before the modulus its power is a square and q square. Okay, a square and q square. After giving the modulus, it will become aq. So the modulus is doing what? Modulus is absorbing their power. Okay, absorbing their power. It can be cube also, like a cube and q cube. Okay, like a cube and q cube, or it can be a cube whole cube. Okay, a cube whole cube. Okay, so it will also, so the modulus will also, it's a power. Okay, so this is a function of modulus. I hope you all understood. Now, as q is not equals to 0, so q modulus greater than equals to 1, hence a modulus is less than equals to b. Now, the main question comes, we have to understand the proof for the conclusion part. Okay, this is the time to understand the conclusion part. So the conclusion is a very tough part. We all know conclusion is a very tough part. We have to understand. Okay, there is any other option. So, okay guys, note it down. Then we will move to the solving part. Okay. Okay, guys, I hope you done. So now we are heading towards the solving part. Okay, the solving part is actually critical. Okay, so here they showed that a by b not equals to 0, b not equals to 0. That means it is not infinity. If b is 0, suppose if they told that b is equal to 0, that means a by 0. Okay, a by 0. That so Ramanujan told us that if a by 0, that means a will become infinity. Okay, a will become infinity like this. But in this case, b is not equals to 0. That means b is greater than anything. B is greater than 0. Means anything, any number. Okay, 1, 2, 3, 4, 1 to 10, 10 to 20, any number. Okay, be it 100, any number. So I hope you guys understood this line. Now let's then b is equal to aq. Okay, b is equal to aq and q is not equals to 0. Q is not equals to 0. Q is not equals to 0. So okay, yeah. Okay, if q is not equals to 0, that means q is greater than equals to 1. Is q is greater than equals to 1. So we can write it as, so suppose we can, we all know that modulus of b is equal to modulus of a q. Okay, that means modulus of a into modulus of q. Okay, modulus of a and modulus of q. Modulus of A and modulus of Q. Okay, here Q is greater than equals to 1. Now we can say